So hello everybody and welcome to today's webinar. Today we'll be comparing advanced design techniques between SOLIDWORKS and 3DEXPERIENCE CATIA. We will be focusing on surface and hybrid design, building assembly constraints to build mechanisms, as well as the application of standard components into an assembly. Our GoToWebinar interface has a questions box that you're more than welcome to use throughout the webinar. We will do our best to answer your questions during the webinar, but we will be saving some time at the end to address any questions we could not get to. We also have some polls that we'll be posting on the interface. If you'd like to participate, you can use the polls function on the GoTo interface. The questions you can vote on are: what products are you currently using? So SOLIDWORKS, CATIA, AutoCAD, Inventor, or other. And are you having any issues with your current CAD package, such as large assemblies, surface design, motion requirements, or other?
So I've gone ahead and opened up one of the polls. So if you guys could vote for those. So far we got SOLIDWORKS in the lead. A couple CATIA, all right. A couple others. I will give you a couple more seconds to finish voting, and we'll go ahead and close the poll. And let's go ahead and share it. So you guys should be able to see what the poll looks like right now. And then let's go ahead and go to the next poll.
And yeah, I jumped the gun on that a little bit, read them both at the same time. I'll just reiterate. So are you having any issues with your current CAD package, such as working with large assemblies, doing advanced surface design, sweeps and blends, or motion requirements, or other?
So we got some motion, some large assembly. It's like large assembly is winning this one. And we got one surface design, two, got a couple others. All right, we'll go ahead and let's give you guys another minute or two, or a couple seconds. All right, so there's the results on that one. So I'd like to thank you for that.
All right, some quick introductions. A little bit about me. My name is Tim Ramos. I'm a senior CATIA specialist with GoEngineer based out of Denver, Colorado. I graduated from Rensselaer Polytechnic Institute in 2014 with a degree in mechanical engineering and materials science. Afterwards, I worked with Honda R&D designing the upper body of vehicles, focusing on surface design. And in 2018, I transferred over to the application engineer space, and I've been focusing on all things related to CATIA V5-6 and 3DEXPERIENCE CATIA. And in my free time, I enjoy all outdoorsy things, as most Coloradans do, like snowboarding, rock climbing, camping, and outdoor adventuring, and also spending time with my dog. And now I'll turn it over to my co-presenter, Darcey.
Hi guys, I'm Steve Darcey. Received my mechanical engineering degree from UALR, and for the past 12 years been working and living in Austin, Texas region for GoEngineer as a lead applications engineer. My colleagues would say I'm an expert in 3D design, but I try not to give myself that title. That way I'm always kind of striving for it. I do like modeling things, making them real, robotics, automation, Arduinos, computers, software, 3D printing. I run quite a bit, so I don't have to diet, but mainly I like anything techie and nerdy. All right, so real quick, who is the GoEngineer? We are the #1 technical resource worldwide for SOLIDWORKS and Stratasys products, and we have a very strong software portfolio for all your engineering and manufacturing needs. We have a lot of locations nationwide, which means it's better for sales and support for you guys. On the average, tech support is about 12 hours per day for your locations. If you're Central Standard Time, it's 7 a.m. to 7 p.m. Eastern is 8 a.m. to 9 p.m. and Pacific is 5 a.m. to 5 p.m. Anyway, we're big on service and big on tech support. On the hardware side, we sell and support the best 3D printing technology out there for production use. Our main products are the PolyJet and FDM printers by Stratasys, and we also carry other products for dental and stereolithography printing. If you need to print metal, we also carry Velo 3D for your larger prints and Exact Metal for less expensive kind of entry point and build size. Both of these can print materials like titanium, aluminum, copper, tool seals, and more. For reverse engineering and inspection, we carry a wide array of 3D scanning products, which can have an accuracy up to 0.01 millimeters. That's 4/10,000ths of an inch. That's pretty small. We carry the Artec 3D series. Here shown, we have the Leo Artec 3D. We also carry the Creaform HandyScan series and the Peel brand, which is a lower entry point of 8.5 thousand, and accuracy is a little bit higher, of 0.25 millimeters. All the software, hardware, training, and services information can be found on our website. So just go there often because we update the website a lot. You can also log into the GoEngineer customer portal to create and edit your own tech support cases. Look up your SOLIDWORKS serial numbers, CATIA serial numbers, pay your bills, get quotes, and also access the knowledge base, community, and forums. All right, now down to the software side. On the software side, most of our business from GoEngineer is selling and supporting the SOLIDWORKS for design software, but we also, of course, support the CATIA line of products. If you want simulation, we have SOLIDWORKS Simulation and Simulia. These support offerings for statics, dynamics, flow simulation. On the manufacturing side, we have SOLIDWORKS CAM and CAMWorks. On the Delmia side, we have an entire suite of products that not only include the CAM, but they also include shop floor software and optimization. And then for PDM, PLM, we have SOLIDWORKS PDM Standard, PDM Professional, and Manage. And on the CATIA side, we carry the Innovia line of software, which can be installed on-site or on cloud, which is pretty much built into the 3DEXPERIENCE platform. All right, digging a little deeper into the software, SOLIDWORKS has a desktop version, which everybody pretty much uses. But we also sell one called SOLIDWORKS Connected, which is pretty much SOLIDWORKS, except, of course, when you save the files, all the files and stuff are managed on the cloud in the 3DEXPERIENCE platform. And then likewise, CATIA side, we have CATIA V5, which is the desktop solution. And then we have a newer interface of 3DEXPERIENCE CATIA, which does have a local installation, but when you save it, it manages everything directly to the 3DEXPERIENCE platform. And today we're going to be demoing the desktop SOLIDWORKS and 3DEXPERIENCE CATIA. All right, so we're going to be demoing this robotic arm. We're going to start off with some surface modeling on the base part. And when you watch this, you're probably going to be like, oh, I could totally do that with solids, but we thought we'd take it a little bit more advanced and just show you some surface techniques. Once we put the base together, then we will assemble the robot arm components and add some cool tips and tricks along the way and finish it off with a quick animation using Make Controller. All right, so let's jump right into it. So I've got some sketches and I'm gonna go to the surface tab and just do an extrude surface. So pretty simple. Make that about 4 inches there. And then we'll do the same thing. We'll just select on this circle. I'm not going too much into the sketches. Those are pretty simple. I just need to make sure that this extrude is up above that little tombstone profile. And then same thing. We'll go grab that profile, that sketch, and extrude that out. This one doesn't have to be quite as far. So make it about 2 inches. And then we'll rotate around. I need to fill in the back face. So I'm going to pre-select that sketch again and go to planar surface and just hit OK on that. So I got a flat surface on the back end. That looks pretty good. So we'll go into trim surface. This I'm going to change to a mutual trim, which means I can select all the surfaces up front and then tell it whether I want to remove or keep. I'm going to tell it to remove. So you can quickly see how you can get rid of them. I need a hole on the inside, so we'll pick out those other 2 faces. And that looks pretty good. So we'll say OK. And there's still surface bodies. So I'm going to go to the thicken command, select all the surfaces, and just say create closed solid from enclosed volume. So what that's doing is changing it so I have one solid body. So this is one side of my base part. Let me go ahead and turn some things on and off. And we're going to sketch on the that plane. I'm going to go steel convert entities and let's get the line command. We'll draw some lines. Put one more out here. Let's go into dimensions. If you saw that, you might have barely missed it. I did mouse gestures, so I'm gonna right click, make that 3 1/4. And then I want to add a relationship between this and the plane. So rotate that a little bit sideways, make that coincident. I'm going to turn on my main diameter sketch and then make this a pierce relationship. There we go, that looks good. And then we'll do a spline between the top and that entity on the right. Let's make those tangent, and we'll make the top one tangent 2. That pretty much fully describes the spline there. We'll turn those guys to construction. They're not going to be used for my revolve surface. So now we'll do revolve surface. We'll pick on the center line. And I just want to make that 180 degrees. Let me rotate around a little bit so you can kind of see what that looks like. It looks good. So I'll say OK. And then on the back surface, I need that to be just a planar surface too. Just fill it in. There we go. Say okay. Let's hide some sketches real quick. I'm going to go ahead and hide the side body. We're going to do some work of cutting some of the material. But before I cut the material, I've got to center it up a little bit. All right, so we're going to do a new sketch on the front plane. Just draw a quick little L with 2 lines. And let's go ahead and dimension that. So make that guy 2 inches, 2.25. Make this one 0.75. There you go. And then just to fully define it, I'll just add some geometry or some dimensions just to make sure that the lines go fully outside the surfaces there. All right, and I want this to be mid plane. So, and I just want to make sure that it's going all the way outside there. So we'll just make it 7 inches just for fun. All right, so that's one part of my surface. Now I need a second part. So I'm just going to get the line command again. Drag that on out. Let's add a constraint, make those 2 things horizontal, or I'm sorry, vertically aligned. And then I'm going to pick on this little edge, make that coincident, and then the line and that edge and make those collinear. So then I fully define the sketch without having to have any dimensions or anything. This one is also going to be mid-plane. It's going to be 3.5 inches. Let me go change that to mid-plane. Say okay, and that looks pretty good. The little bulb part is in the way, so I'm going to hit tab to hide. That'll hide the surface body. And then all I'm going to do is steal these 2 edges. So we'll use convert entity, and that's going to be what I'm going to use to extrude. And I'll extrude those up to a vertex and pick on that little endpoint. And there we go. Now I need to trim the inside out of that. And in order to do that, I need to knit the two of the surfaces together, or 3 of the surfaces together. So let me pick on those 3, say okay. And so now when I go to trim surface, let me go turn that guy back on. And we're going to do a standard trim. And I just want to get rid of that little inside area there. There we go. So that's kind of the area that I'm going to cut away from the revolve surface. All right, so I'm going to turn the revolve surface back on. We're going to do a mutual trim. So I'll pick all the surfaces there and then just tell it to remove and select the parts that I don't want. And that's looking pretty good. I like that. So let's hit OK. And I think I've got everything I need. We can go ahead and stitch that into a solid. So I'm going to do knit surface and pick all the surfaces and just check the box for create solid. So it creates an enclosed solid. You'll notice all my surfaces are gone and I just have my 2 solid bodies. So I'm going to right click on those, do a combine and add. And now I just have 1 solid body. And I'm going to go and save off in, of course. Let's go to the add some fillets. We'll make that 0.1. And then I'm going to select on the little edge, and don't move your mouse too much, and you get this little toolbar. And then this will allow me to select a whole bunch of edges. So I'll get 24 edges right there. I still need the inside of the hole, so I'm going to pick that as a face. That looks good. I think I've got them all. So we're going to say OK. And then with that done, I think we're ready to go ahead and do a mirror. On the mirror, I don't want to do features to mirror. I want to mirror the entire body. So we'll go to bodies to mirror and pick on the body. Then I'll go to mirror face and plane. Now I could just pick on the back face, but I'm going to pick this out of the browser tree. So I'll pick on the right side plane. The preview looks good on there. And I also had merged solids. And so you can kind of see now we have just 1 solid body all put together. I need to put a motor mount on the side of this. So I'm going to drag off a plane. Let's go make that 3.125. So now I can sketch on that plane. So pick on it and do a new sketch. And I'm going to steal the inside circular edge of that hole there. And then I'm also just going to draw a circle starting at the center. And then let's do mouse gestures to get a dimension real quick. There we go. And place that. And let's make that 2.125. And we're just going to do a regular solid extrude. We'll rotate around a little bit. Preview is always nice on these because you can see what you see is what you get. On the direction, I'm going to say up to next, and that looks really good. So we'll say OK. All right. Turn that guy off. We'll pick on the little edge. I want to put a fillet on there. And 0.1 looks good, so we'll say okay. And then the last thing I need to put on there is the bolt holes for the motor mount. So in my design library, I've got a little feature for my NEMA 11 motor mount. So I'm just going to place it on that face. The thing wants me to select on a circular edge, so I'll pick on that edge, hit OK. And now I've got my 4 bolt holes. Last thing I'm going to do is make a mate reference. So when I drag a motor on there, it's going to automatically stick to the apply the mates. So I'm going to use the edge, and then I'm going to use that bolt hole, change that to concentric. And the reference name for NEMA 11 is very important there. All right, so that looks good. Let's go ahead and tile. I'm going to drag and drop that guy into the assembly. I'll go ahead and close out of the part and maximize the assembly window. And we're just going to use some mates. So I'm going to pick on the 2 cylindrical faces, make a concentric mate, and then pick on the face, hold down Control, and then that's when the little dialog will pop up, and we'll do coincident there. All right, so that thing can now, all it can do is rotate now. Let me go and reorganize that in the browser tree. I like that to be nice and straight. And we'll just pick on the front plane, and on the base, we're going to pick on the front plane of that one too. And we'll do an angle constraint. And it's close to 5. Let's just put 5 in there. That looks good. And that one is going to be controlled later. So I'm going to go ahead and name it and put robot in front of all these things. So I'm going to say robot base. And that looks good. And then let's go and find, now I want to do kind of the same thing. We're going to mate up the arm. So I'm going to do concentric. And then this one, I'm going to move it just a little bit, just to make it easier for picking on some of the faces. But I'll pick on 4 flat faces, 2 from one part, 2 from the other. Not that one, that one. There we go. And I'm going to use the width constraint. So the width is going to center those things up. It keeps me from having to go in the browser and find the planes for the center planes and stuff. So that looks good. I'm going to hold down Control and drag and drop another one in. And we'll kind of do the same thing. We'll do concentric. This one's a lot easier to pick, and we'll do the width. There we go, it's centered up. So that looks good. Happy with that. Let's go ahead and do the third arm there. So we got concentric, and that one's a little harder to pick. Let's get width there. All right, so it's centered up. It's not moving the way I want, so I'm going to right click on this guy and go to fix. And you'll see some of my mates in the browser tree are kind of messed up right now, but I'm totally fine with that because I'm going to change it later. So we'll again do concentric and then face to face, coincident. So now that thing can revolve a little bit, but it's placed where it is. So let's go ahead and float our arm. That way our mates are all happy again. And we're going to add some other mates to control, or angle constraints to control the arms. So that one's pretty close to 135. Let's put that dude in there. And same thing, we're going to go in there and we're going to rename these things, call them robot. And that's our first arm. So I'm going to call it robot arm 1. There we go. If I can find the keyboard for 1. So that looks good. All right, then we got to go from one arm to the other. And oh yeah, I dragged and dropped that one. So that one's at the bottom of the tree. So let's pick on that one. So the front plane, there we go. It's close to 120 degrees. So we'll just accept that. Again, we'll rename it. This one's going to be robot arm 2. All right, and then I get a little crazy. I got to drag these things around so they're in the right order. All right, and then we go to face or plane to the front plane, do another angle. Now it's close to 150. And again, rename it. So this one's a little bit redundant doing these, but works pretty good. So robot arm 3. Now from the arm 3 to the end effector, I'm going to go ahead and put an angle constraint so I can rotate that around. And I'll make it pretty close to straight, make it at 5 degrees. And again, we'll call that robot. That's the grip, so we'll call it grip rotate. I like that. All right. Now let's take a look at the motors. So I'm going to open up this NEMA 11 motor, and I want to show you that on the mate reference, I do have a mate reference on here. And again, the name is particular. So NEMA 11, I'm picking the same type of edge, same secondary face with concentric. So what that does, let me rotate this up just a little bit, is I'm just going to hold down Control and drag a new one in. And you'll see it automatically pops in there. So then I can hit the Tab key on the keyboard and that'll flip it. So that looks good. So then I can go to all my other areas wherever I have that motor mount. I'm going to just drag it. And whenever I get close to some of those holes that aligns to, it'll automatically snap into position. All right, then I also have a NEMA 8. This one, of course, is not called NEMA 11, so I got to make sure that on the back side of that one, I have one called NEMA 8. So I have to have them on both the part that I'm putting it to and the part that is going to. All right, now all I got to do right now is let's rotate this around, zoom in here a little bit more. I got to fasten the fastener so the thing doesn't move. So we're just going to do a coincident relationship and let's drag it into the part. Now this is a smart component. So if I right click on that, I'm going to say insert smart features. And I'm going to pick on the top face of the gray part right there. Just say okay. And it's going to automatically put in the right counterbore size hole for this. And this is pretty cool because if I move that around and hit rebuild, you'll see it actually moves inside that part. So it stays up to date. Now I'm going to go ahead and just make those concentric. And that hole does live in the part itself. So let's go ahead and open up that part. And I need to put it on the other locations, that circular pattern. So I'm going to drag it up in the tree above the circular pattern and just edit the feature. We'll pick on that part. And now we have the hole in all 4 of those locations. So we'll save that and close it. Now it's up to date in the assembly. And I just need that same pattern for the bolt. So I'm going to do a pattern-driven component pattern. And we'll just pick on the seed for that. And so that way it's actually going to the pattern at the part level to update. So you can kind of see if I change this, I got a 4, change it to 5 and hit rebuild, I'll get 5 holes and I'll also get 5 bolts or 6. I'm gonna go back down to 4. That looks good. All right. Looking real good. All right, last thing I need to do is just do the make controller. So this is pretty fun. I'm going to go look at my browser tree. Let me collapse a couple of these things and go into the mates and anything that says robot, but I want to do them in order. So I want the base first. There we go. Robot base, arm 1, arm 2, arm 3, then the rotate for the grip. And then the last thing is the actual grip itself, which clamps together. All right, so I got them all selected. You can see them in the dialog box. And when I do, it gives me little amounts that I can change these and it'll tell what the position is. So you can see as I start to click these things up and down, it's changing the degrees that those angles are at. And it's going to remember those for the different individual positions. So here I'm going to open up the robot grip. We're going to act like we're going to grab something. So I'm going to start in the open position. So we get there at 137, and then I'll start a new position. So I'll just call it position 2. And then I'm going to clamp that thing. So I'm like grabbing something. And that's going to be it for position 2. So we'll go to position 3. And then we'll start kind of cranking this guy up a little bit. We'll lift the part. You can kind of have some fun with it. Add another position. There's also a lock and unlock button. So if I want to unlock it and just start dragging it around, I can. So that's kind of a nice little tool. We get position number 5. Let's go ahead and rotate it around. And position 6. And you can move, multiple angles at the same time, and then we'll see it in a little while when we calculate it. It'll kind of kinematically go from, 2 of those angles at the same time as it's rotating. All right, let's rotate that grip a little bit. And then now we're going to drop the thing. So we're going to use the robot grip to open that thing up. And that'll be position 8. All right, so then down at the bottom left, we're going to hit the little calculate button. And all it's doing is going through position 1 to 2, 2 to 3, 3 to 4. You can kind of see it going on the little animation. Drop that down and you'll see it start to open back up. I can hit the reciprocate button. So then it's actually doing this in reverse now. So it can act like it's going to go over and grab another one. except of course I would have wanted to open up before I closed it. And that's pretty much it. All right, so I'm going to turn it over to Tim. He's going to do a 3DEXPERIENCE CATIA demo. So let's see what he's got.
So just like Darcey, I'm going to be building this base part for the robot arm assembly in CATIA 3D Experience. Then once I build it using surface design techniques, I'm going to be inserting it into the root assembly, applying engineering constraints or assembly constraints, and then I'll be turning it into a mechanism where I can control each constraint individually. And then I'll be applying standard components to this model using smart mechanical components. Then I'll round it out by animating the mechanism. So in this model here for this base part, we can see that it's pretty much symmetrical. So I'm going to once again use surface design techniques to build one side of it, and I'll symmetry it about the ZX plane, and then build in the symmetric parts afterwards. So using my generative shape design app, I'm going to hide my part body and unhide my geosets, where my geosets will contain the majority of my wireframes and surfaces. The main difference between geosets and part bodies is geosets are unordered, meaning each command that I put in place will not consume the one before it. So any inputs that I use, I can reuse them throughout the model. So here we see some reference geometry. We have a wireframe representing an axis and a semicircle representing the outer diameter of the part. I'm going to extrude this arc and use it as the outside of our axle mount. And next, I'm going to build a flat wall using a line and an extrude to define the inside of our axle mount wall. So first, I'm creating a line using a point and extruding it direction in 3D space. And then I'm going to adjust the Y position of this line by using my parallel command and referencing it to a plane. Finally, I'm going to define the surface or create the surface by extruding this wireframe in our Z direction. So I've already gone ahead and created other surfaces to finish out this portion of our model, and just using the same techniques as I did to make the surface we just saw. I'm also going to unhide a cylinder that represents the axle of our base part, and I'm going to use first our shape fillet command to build the arc on the top of this axle mount, where a shape fillet will essentially, it takes our surfaces and trims them and fillets them simultaneously. Here we have the option for bitangent and tritangent. I'm going to use a tritangent fillet to just create an arc between these three surfaces. And because trim commands have multiple different solutions based on what side you're trimming on, I just have to toggle these arrows to make sure I'm trimming in the correct direction to get the desired resulting fillet. Now I'm going to define the rest of my axle mount by using a trim command and trimming these surfaces together. So the general rule of thumb or the general method when using trim is to select the portion of the surface you want to keep, and it'll automatically give you the solution you're looking for. Now, if we chose different portions of the surfaces, we'll notice that we don't get the desired result, but we can still toggle through our different solutions. Finally, I'm going to create this hole to represent the axle, and once again, toggling through my solutions until I get the desired result. So now we have our axle mount surface, as we can see here, referencing the final model. And now I'm going to build the center portion of this. I'm going to hide the geoset for the axle and now work in the geoset for the center. So the nice thing about geosets is we can rename them, so it's better for organizational purposes. So here, like I said, we're reusing this arc that represents the diameter or the radius of our base and just extruding it in our Z direction. We are also utilizing this spline in our central axis to revolve the spline and build us our hemispherical surface. Because these are two separate entities, I could use a join command to combine them together and make them one singular surface. Unhiding these other extrudes that I've made in a similar fashion to the extrudes earlier, I'm going to utilize these surfaces to build the cutout so we can accommodate the shape of the axle mounts. And then just showing the shapes against the final model to give an idea of which walls they are coinciding with. I'm going to be trimming these surfaces together to make one congruent shape. I'm going to be creating these one by one, just using a trim command one after the other, adding a new surface to each trim command. Now, keeping that in mind, we can use more than two surfaces in a singular trim command, but in the case where we might have to update this model down the road with the possibility that our solutions might switch, it's just easier to correct that scenario when we just do the trims one by one. So here we see toggling through our solutions until we get the desired result. Unhiding our axle mount, we can see that we fit this geometry sufficiently. Now I'm going to trim these surfaces together to make it one singular shape and remove the overlapping surfaces. And because this is symmetric about the ZX plane, I'm going to symmetrize it. One singular surface. Now comparing this to our final model, we see on the left-hand side here, we see this cylindrical surface used to mount our motor on that axle. So here I'm going to build that geometry and use my Boolean commands to insert it into the final volume at the end. So here we have our reference cylinders that represent the outer and inner diameters of our motor mount. And I'm going to use my split command to reduce the size of these cylinders so that they'll sufficiently fit in our model. I'm going to utilize the compute intersection command, which will output a wireframe that represents our split. And we're going to use these wireframes down the road to create some more surfaces. But first, we're going to utilize our other reference representing the inner diameter of our axle and split it and use compute intersection. Now I'm going to utilize fill so I can connect the surface between the outer and inner diameter. And I'm going to use those output wireframes as my reference geometry to create this fill. And finally, once again, these are all separate surfaces. So I'm going to use my join command to make it one singular surface, allowing us to use a close command to create a volume. Now I'm going to create a new part body that I'm going to place this motor mount into and rename it motor mount, just to make it easier to organize our tree and find this geometry down the road. I'm going to switch over to my part design app where I have the functionality to create solid models. I'm going to use closed surface. It's going to do exactly that. It's going to close this surface and turn it into a solid. And I'm going to work under my primary part body and deleting out the old model. I'm going to unhide my symmetric base geometry. And I'm going to once again use closed surface to turn this surface into a solid. Now I'm going to use a Boolean trim command, which will allow us to insert this motor mount into the base geometry while removing any overlapping geometry. I'm going to choose some faces to keep just to ensure that my result is as expected. So now we have incorporated the motor mount into our base. I'm going to finalize the part by adding some fillets to our sharp edges. I'm going to use the auto fillet command to apply a common fillet radius to every sharp edge, minus the ones that I've deemed as functional faces. So when I select functional faces, any sharp edge that is connected to those faces will not have a radius applied. Hitting preview, we see that's true. And you hit the OK button. That change. So now that I've finished my base part, I'm ready to insert it into our root assembly. I'm first going to hide the wireframes that are not relevant for setting our assembly constraints, while leaving the ones that are relevant in our showing view. I'm going to switch over to our assembly design app. And I'm going to right click on the root and choose Insert Existing Product. And now with this filter option, I have the ability to either select a model from our session or search our database. I'm going to select the model from the session since it's already open. You see the model inserts at the datum of our assembly. And I have the option to move the geometry around or move the part around to position it. And then next, I'm going to set what's known in SolidWorks as our assembly constraints, but known in CATIA as our engineering connections. The primary difference between engineering connections and assembly constraints is the engineering connections are set up so we can build mechanisms and animations and simulations down the road. So engineering connections have certain types of connections that allow for certain degrees of freedom and certain type of movements. But beyond that, it's set up pretty much just like assembly constraints. So set a contact constraint where I will snap our base to our base plate, and then a coincident constraint where I'll snap the center axis of our base to the center axis of our base plate. And finally, I'm going to apply an angular constraint, which will allow us to rotate the base around the base plate. Setting it to controlled will allow us to control this constraint physically and adjust the angle on the fly using the slider. So here I just set an angle between each of the parts respective ZX plane and just set the lower and upper limit to 0 and 360 respectively. And setting a specification for check contact. So if we do an interference simulation down the road, it will check for this contact constraint. Now I'm going to set the assembly constraints between the lower arm and the base. And effectively, I just want to position it and then make it so I can adjust the angle using my mechanism or my commands. Here we're going to integrate that using, once again, an angle constraint and choosing these relevant planes between each part, changing it to controlled, and then setting the lower and upper limit as well as the current angle between these planes. So now that we've set up all of our assembly constraints and built in our degrees of freedom, we could then go into our manipulate command. And with free manipulation and with respect to constraints checked, we have the ability to drag around our model and have it move within its degrees of freedom, just like we would be doing in SolidWorks. To expand on that, we could also create a mechanism where we can specifically control each constraint. Switch over to our mechanical systems design app to build this mechanism. I'm going to create a mechanism representation. Inside of that, we have joints and commands, where joints allows us to include or exclude any of our engineering connections or assembly constraints, as well as the commands that we're controlling. Finally, we can also include mechanisms that are built within subassemblies. So in this model, we have a subassembly for the grabber. And if we include this, it will allow us to have a handle or a slider to adjust the grabber at the same time that we're adjusting all the mechanisms at the root part level. So those joints all create commands. In here in our command window, we can see we have sliders for all of the engineering connections that I have created a controlled constraint for. And we'll notice at the bottom of this window in its own section is the grabber mechanism. And we can see that we can successfully control that even from some level. So to finish out the model before we animate it, I want to add in our standard components. And here I've created 4 separate what's called anchors defined by Axis systems that will accept a cap screw, which is also defined by an Axis system, and also has a volume that will be removing from whatever model it gets applied to. So we'll switch over to Smart Mechanical Components app. And we'll just note that each of these anchors that I've created, they're once again defined by an Axis system, but also defined by a part type. So this anchor will accept only cap screws. So the standard components I've defined as a cap screw. So when I go and place a component on here, it's looking for cap screws and will also allow me to propagate cap screws to the rest of the anchors that should accept cap screws in this model. So clicking on the anchor, I get a context menu allowing me to search on a product, which I can once again click on from in session or from our search. Here's searching it from in session or clicking from in session. We see we get a context menu that allows us to adjust the orientation, propagate the cap screw to all other anchors that can accept them, as well as apply impacts, which we'll see once we accept this, that will cut out the volume or cut out the material needed to accept the cap screw. Once we hide the cap screws, we'll see that that volume is indeed cut away. If we go into our base plate model, we'll see that that cutaway or that those pockets are applied directly to our tree. So I'm going to perform a similar action of inserting a standard component, but I'm going to apply it to the base, and I'm going to apply the motor, and it's going to create at the same time these drill holes to accept the motor, where the drill holes are represented by these purple volumes here. So the only difference here is that I've defined this anchor as well as the motor as a user component. So instead of looking for cap screws in this case, it's going to be only accepting user components. I'm going to apply the motor in the same way that I've applied the cap screws, as I'm going to select on the anchor, use my context menu to bring up my filter to search on a product or select a product from session. On selecting the stepper motor, we'll see that it is aligned and oriented correctly. We're also making sure we choose impacts. We'll notice that those drill holes are indeed now applied to our base part. And now that I have finished our entire model, I'm ready to go and build an animation of the mechanism. So to do that, I go to Mechanical Systems Experience. We see we have the option to create a mechanism, which I already have. So we're just going to create a kinematic scenario here. And within this app, we create simulations that deal with force, reactionary force, gravity, friction, etc. But in this case, we just want to make an animation. So I'm going to use the excitation recorder. And we'll see what this does is where it brings up our mechanism sliders, as well as a record button that allows us to move our assembly, and between each record button that I hit, it'll take all those movements and compile them together in a smooth transition. And now we're just going to fast forward through the rest of this setup. And after I compile the results, in this case, it's just compiling the recordings. In other cases, it would be solving, your forces, etc., and getting results. Here, our only result is the animation. Here we see the animation run.
All right. That was cool, Tim. That was some good stuff. Like seeing kind of a little bit of the comparison between the two products for sure.
Absolutely.
All right. So a little bit about the contact information for us. And then please sign up for our email newsletter so you can stay up to date. We only email you once a month, so we're not going to spam you. And it'll let you know on any of the upcoming webinars. December, we should have one on large assembly performance between SolidWorks, 3DEXPERIENCE CATIA, and CATIA V5. So that one should be a good one coming up. You can find out more about our professional training, including SolidWorks and CATIA, with that link. And you could, of course, subscribe to our YouTube channel, where we have thousands of videos on tips and tricks with all of our products. Don't forget about the GoEngineer customer portal for tech support, serial numbers, and more. And just want to thank you guys for coming out to the webinar. Hope you have an awesome day.